All right, how's it going today? Questions on the midterm or PA3 or even Java?
How much questions total are there on the midterm?
How much what?
How many questions are there on the midterm?
8 questions, but each question has sub-questions inside it, kind of like life.
So what's the real answer?
Oh, I don't know, 8 pages.
Oh.
But I left you lots of space to write answers, so.
So for PO3, can we just talk about the AI part of it?
Sure. So the AI does not have to be very I,
Yeah.
right? It can be as simple as,
Pick a random unoccupied square.
yeah, you can pick a random row and column, and if it's occupied, pick another random row and column and do that until you find a place to move.
Oh, they have to try to win?
Couldn't that technically
Hmm?
lock
They
itself?
have to try to win?
No, it can be random,
Okay.
right?
Yes.
Or you can start in the upper left and just move through until you find a spot to move and grab that spot,
Eventually
right?
it'll-
Just make sure that before you do anything like that, that there is a place to move, right? Make sure the game isn't over, or you'll get stuck in a loop forever. But yeah, it does not have to actually be making informed moves. It can move randomly.
So I know that when you do the win conditions is to check like every possible combination of the win, like check are these 3 squares and then check are these 3 and then check are these 3 and then same thing
Mhm.
for every individual square. But
Right.
basically, is there a more efficient way to do that?
You start from any known x you find and say, is there a row connected to this x, rather than checking every square.
That's another option.
That's a lot faster, but it could be a little faster.
Okay.
You could also assign prime numbers to every square and take the product of every square with an X and just record all the possible products that correspond to winning.
Anything that would make it so I don't have to write out hundreds of.
You can go to great lengths to avoid writing a bunch of if statements.
Yeah.
But there's really nothing wrong with writing a bunch of if
No,
statements
there's
either.
not. I was just wondering if there's a more
That's
an easier way.
What are you looping over the rows and columns already? What? Are you looping over the rows and columns? So that we're using the same code to give each row
I mean, I'll figure it out.
Yeah, so to know if somebody won horizontally, right, you have to know if
Oh, is the row all that?
0, row
Yeah.
r comma 0 equals r comma 1 equals r comma 2 equals x or o, right? You can do that for all 3 rows.
And for columns.
And then do the same thing for columns, and then there's 2 diagonal checks.
I was wondering about the first main stage where you pick equals was what
Mm-hmm.
X and O's to pick. Are we supposed to build a new J-frame for that whole stage, and then when it goes next, it loads up the tic-tac-toe J-frame part?
You can do that, or you can,
So my main question is how do I make a blank page for that screen of picking your options and then switching it to the game?
there's a few choices. So you're probably going to have a J-frame on top of everything. And you could put your options over here. And if you want to have like a game difficulty option or whatever, right? And while you're doing this, you can have a field sitting here with no marks in it, right? That's totally valid. And if they click here before the game has started, right, tell them you've got to start the game, and some kind of start button or something to actually begin playing. Or you could simply not draw anything in that area of the J-frame, right, that panel, until the game has started. Or you could gray it out or something if you like. Or you could, when the person clicks start, create an entirely new J-frame that just has the playing field, the tic-tac-toe board in it, and all the clicking and painting takes place in that. And when that's finished, you can close that and come back to here. So you have sort of a control panel here, and then when you play the game, a new window pops up as you play in that.
Yeah.
Totally up to you.
Kinda like
Okay.
Minesweeper.
Like what?
Kinda like Minesweeper.
Yeah. And you're welcome, depending on your schedule and energy level and so on, to either make this as simple as possible or make it as interesting as possible for yourself, or find that sweet spot, right? I think doing it like this with a J panel here with a board that just doesn't have anything drawn in it yet is pretty straightforward compared to other options. But, you know, it's an excuse to explore and play around with these things. And you might come up with several different versions of this before you actually submit it, right? That's okay. You can come up with more than one solution and then submit whichever one you think you like best.
I like that, when you talk about the prime numbers for this
Yeah.
game, because you could do like 2, 3, and 5 for the top, and then and have like whenever you place a thing, multiply product by that number.
Yeah, yeah.
And then see if that product is divisible by 60 for the top row. So that'd be 2, 5, 2, 3, and 5. And that way, I think that way, because they're all primes, there's no
True.
second
Yeah.
60.
Right. Yeah, so just record all the divisors for when somebody's won. That's cool. Yeah, it's
Use
kind of
one
a-
if statement instead of
Yeah,
30.
yeah.
Oh yeah, 1 instead of 3, 9 instead of.
Mm-hmm. And it's an excuse to put primes in your program.
Exactly.
It might look like magic numbers though.
Yeah.
Yeah, that is true.
Although you could put those in a static variable.
True.
And also add powers of 2 and count the like.
Yes, you could add powers of 2 instead of multiplying primes.
Yeah, that would too.
Which is somehow like a really good thing to do, because when you add powers of 2, you're really just coding integers into binary, which is kind of what we're doing anyway. But I wonder if you can actually apply that to Gödel's proof of incompleteness. Again, we're wondering. 'Cause that's where multiplying primes comes in, to convert arithmetic proofs into integers. So why not just add powers of 2?
So you just come up with $1 million idea.
You did. Interesting. Okay.
But yeah, wait, you could like sort of mask for like each one, and you just loop over it and it equals not 0.
Right. Yeah. All right.
Like that might. There's more than one piece. So.
Yeah.
I read that's the thing you do, if you want to have a game tiles that connect, you can have adjacent tiles as primes, and you can just see the primes.
Mm-hmm.
And that way you know what tile to strike. And that's what we have.
You could make objects who communicate with their neighbors
Well, that's true, you can do
up,
that.
down, left, right, and diagonally.
And that'd be good for the computer, because then you could give it kind of a danger
Yeah.
sort of state. So the
You could
computer
measure the
would better.
connectivity strength from one side of the
Yeah.
field to the other. Which means you could probably teach slime mold to play tic-tac-toe, which is also good. All right, other questions? Well, let's continue talking about trees. Everyone loves trees. So we did a motivational setup for this yesterday, right? We looked at some trees and we talked about ways we could balance them by taking things that were heavy on one side and doing that, or taking things that were heavy in this way and doing this, right? So let's formalize some of this, and I'm going to put this stuff on the board so I don't have to keep putting it on the projector. But this is basically how we're going to balance trees. So remember, we're talking about AVL trees here. Okay, these are balanced binary search trees. And so a few possible scenarios. One is when we're oriented like this and we're looking at balance factors, and here we have a balance factor of -1, and here's a 2, and this is an unbalanced tree. And if we just added a node and we're working our way up, and this is the first node we hit with a balance factor of 2, then we know this is where the imbalance happens. And we can change this into this. And that's still imbalanced, but then we can change this into this. So this is a left-right imbalance, this is a left-left imbalance, this is balanced. And the only details missing here, which are up there, is what to do with the children of these nodes. So let's give A a child, which we'll just call 1, and let's give B its left and right subtrees, which we'll call 2 and 3, and we'll give C a subtree, which we call 4. And remember, when we make these rotations, we need to preserve the fact that this is a binary search tree. So we've got to keep everything in order so that everything to the left of a node is smaller than the node and everything to the right is bigger. So right now our search order is 1, A, 2, B, 3, C, 4. Where 1 means the traversal of everything in this subtree 1. That'll happen first, and then we'll visit node A, and then we'll traverse this tree, which means we'll visit everything in the subtree 2, and then we'll visit B, and then the subtree 3. That completes the traversal of this left subtree of the original tree. Then we traverse the original root C, and then traverse the right subtree 4. So that's our search order in the original tree. We need to preserve that search order after we do this rotation to make an LL case, and we can do that by assigning the children as follows. So we move 2 from B's left child to become A's right child, because A is coming down here. And then B will continue to have its subtree on the right, and C will continue to have its subtree. And if you look at the search order here, it's going to again be 1A, 2B, 3, C4. So we haven't broken anything. And then when we, so this one we're kind of rotating like this. Here we're taking the B and rotating it to the root and bringing C down. And so when we do that, B's right child is going to become C. And so we need to do something with 3. So A's children stay the same. And we need 3 to become something after B and before C. So after B before C, we can just put it off on the left. So the right child remains 4. And the traversal order here is 1A, 2B, 3C, 4. So none of this changes the ordering of the nodes, which means it's still a valid binary search tree, but this will be balanced. And then just for symmetry, let's do the other versions. balanced tree, and let's see if we can. I'm gonna have to do these backwards. And this one's going to be. This is a balance factor of 1, this is a balance factor of -2, this is a balance factor or 0 or -1, this is -2, this is balanced. And so A is going to have a 1 over here. Don't quote me till we're done. Does that look symmetric? Close enough. All right, so this is our prescription for balance operations. So let's build some trees and let's balance them using this approach. So we'll start with a 50. So that's the root of our tree. We'll put in a 30. That comes over here on the left. This is a balance factor of 0 and 1. We're still balanced. Let's go ahead and put in a 10. So this is a balance factor of 0, 1, and 2. So which case are we in?
Left.
Left, right? Here's a node with a balance factor of 1 or 0. Here's our imbalanced node with a factor of 2. And we don't really need to do this at this stage, but let me go ahead and apply our labels from here. And these subtrees 1, 2, 3, and 4, those are all null, right? There's no children off of A, there's no right child off B or C. So those 1, 2, 3, 4s don't really factor into this. And our procedure just says move B to the root, put C on the right, A on the left. So this is going to change into that. And that's nicely balanced. Okay, so let's go ahead and add a 5. And this is a balance factor of 0, 1, 0, and 1, so it's still balanced. And now let's add an 8. And so this is a 0, -1, and that's a 2. And remember, we're always inserting at the bottom of the tree, right? We inserted leaves when we do binary search trees. So once you insert, you follow your parents up, you adjust the balance factors. If you get all the way to the root and none of the balance factors have been 2 or -2, you're still balanced. But as soon as you get to a point where a balance factor is 2 or -2, you stop right there and you say, okay, we've got to do a rotation here. So we've got a -1 and a 2, so this is our left-right case. So this was left-left. And we can label these again. So in this case, this is C, this is A, and this is B. And again, there's no subchildren involved other than this up here, which is subtree 4, and it's not going to affect anything, right? Because we're just working that's not even true. Subtree 4 is empty. So our adjustment for left-right is to take CAB, move C to the root, leave C in the root, swap B and A basically, and put A on the left of B. So this is going to be the same. Our root 10 is going to stay the same. We're going to swap B up to the root and then take A and put that on the left. That's our left-right adjustment, and now our balance factors look like the left-left case. So this is A, B, C, and there's still no subtrees involved, so we're just going to bring C down to the right child of B. The 30, 50 don't change, so B will become the root, C goes off to the right, A stays to the left. So that's our left-left adjustment, and this is balanced again. Right, and when you're doing this, make sure that it's still a binary search tree, 5, 8, 10, 30, 50. Right? Make sure the order is still correct. That's a good check. All right, so let's add a 7 over here. A balance factor of 0, -1, 0, 1, 0, and 2. So now we've got a more interesting case. So it's that root 30 where we have the imbalance. It's a 2 followed by a 1. That's our left-left case. So let's go ahead and label these. This is C, this is B, this is A, this is subtree 2, this is subtree 3, and this is subtree 4. And so that should be changed into a new tree. I really don't know if this is going to work or not. But with B as the root, A and C as the 2 immediate children, and then subtree 1 is null, so there's nothing to the left here. Subtree 2 comes over here. Subtree 3, which is a 10, comes to the left of C. And subtree 4 comes to the right of C. Five, 7, 8, 10, 30, 50. It's still a binary search tree. Balance factors of 0, -1, 0, 0, 0, and 0. That's a balanced tree. And we can go on. So the idea is do your insertion and then move up to your parent, see if there's a node with a factor of 2 or -2. If there is, see which case you're in. You have a node with a balance factor of 2. If the left child is -1, then you have a left-right case. If your left child is 1 or 0, then you have a left-left case. Same over here. It's -2. So you'll be in one of those 4 cases. And then make whatever adjustment is indicated here. And you'll be left with a balanced situation. So how do you code this? It's really, really straightforward, right? Assuming that you've inserted and you're moving up and you get to a point where you know that this is the imbalanced node, let's say this is temp. Okay, set C equal to temp. C is a node, right? So C equals temp. A equals temp dot left, subtree 4 equals temp dot right, subtree 1 equals A dot left, subtree, or B equals A dot right, subtree 2 equals B dot left, subtree 3 equals B dot right. Those are Java statements, right? And it gives you basically pointers to all these different pieces, and then you can just cobble them together into this, right? Make C the root, C dot left equals B, C dot right equals subtree 4, B dot left equals A, et cetera, and you just glom them all together, and you've got a tree like this. And you pass that to your left routine, and you get back a tree like this. So what we're doing here on paper, right, you can do in code pretty straightforwardly. But debugging it can be fun. So if you try to code this up, right, you definitely want good pictures, okay, pictures that are good for the way you work. You want to be proficient at using whatever debugger you're using, whether it's JDB or the Eclipse debugger or something else, so that at each step of your code, you can see what the data structures look like in memory, and you can compare it to your pictures on paper and make sure that the changes you've made are what you intended. And you either get through to the end and everything worked great, or you'll get to a point where you think your picture should look like this, but the 2 is null instead of being a subtree or something, right? And it's a really good exercise to work on. It's not something I'm going to assign, okay? But I often have students coming up saying, how can I brush up on this stuff over summer? Or I'm not going to be taking more programming classes until next winter. What can I do to sort of stay active with this, right? This is a really good exercise. Code up an AVL tree routine. It can take a while, but it will really, really exercise a lot of these essential skills, right? Visualizing data structures, working with debuggers, looking at things in memory, stuff like that. And when you finish it, it's really good, because then you know you never got to do it again. That's a good feeling. I've done this exactly once. It was an assignment. But if you can do this, right, you can do pretty much anything. This is the essence of working with data structures, right? The details will change depending on the structure, depending on the algorithm, but if you can go between what you want to do in your head, pictures on a whiteboard, and code that implements that, right? Once you've got that connection, then there's no limit to what you can do. So these kinds of things are really good exercises. Questions? All right, I'm going to leave this up, and let's go ahead. How many people do we have in here? Got 12 people. Go ahead and split yourself into 4 groups of 3, and let's do some balancing and rebalancing on the board. So you got 1, 2, 3, 4 whiteboard spots.
I think it's.
Let's take the big one.
So let's start with this tree. That's bad.
So let me give you some nodes to work with.
Only the.
I shouldn't have turned off my projector. Can you see this bottom?
Yeah.
So let's go ahead and let's go ahead and start with that tree. And you wanna write down the balance factor on each node, figure out if it's imbalanced, figure out which case you're in, and then go ahead and apply the rotation or rotations.
So it's, what is it, the balance of the wet minus the balance of the right?
Yeah, and the 7 is right.
Because if, so this would be -1 minus -1. If it's greater than 0 or -2, it's imbalance. This one would be -1 minus 0.
Let's just.
At least have to.
That's 2, yeah, that would be -2.
It's just gonna get.
This would be -2, this should be 0.
And what are we supposed to do for just going to left, right?
I think the idea.
So we wanna go into the left,
It's like
left.
one of these guys.
So that's what it works. So we can go 10, 7, 5. 10, 7, 5.
So this is one of the left, right, I would say.
Oh, that's the tree.
Yeah.
I don't know, this, I guess we're doing that. Oh, it's 57 and 5.
So towards the right,
Okay.
can we?
I guess you wanted me.
Let's shift the 5.
Would it just be 10, 7, 5? I think that's what we wanted.